All right, let's do this. I've got a couple of examples here of series convergence problems. The first one, we've got 7 over n. You can start writing out terms of the series. You might recognize something. You might also notice that this looks kind of like 1 over n. And so remember that one of the things you can do is factor out a constant and create a series that maybe you recognize. So I'm going to factor out a 7. And that's going to leave me with a 1 over n here. So that is 7 times the harmonic series. The harmonic series is divergent. 7 times something that adds up to infinity is also going to be divergent, okay? And we could say it's divergent by the harmonic series test. All right, second one here. If you notice, you're constantly multiplying by 4/3 here. So once again, you could list out some terms and you could figure out that your first term there, I think, is going to be 20/3, and your next term is going to be, I think, 89ths maybe, and so on. But you should be able to tell if you've got a value being taken to a power, you're consistently multiplying by 4/3. This is a geometric series, okay? And because this is a geometric series, we just need to have an R value that's between -1 and 1. And notice here, my R value is 4/3. I'm multiplying by something greater than 1. The terms of this series are going to increase. All right, so you may be able to see that by listing out a few terms, or you may just kind of recognize geometric series at this point. But this is a divergent geometric series. All right, let's move on to these examples over here. All right, this next one here, if you want to, you can factor out 3 and make that 1. It's 1 over n cubed plus 5, okay? You could compare that to 1 over n cubed. Okay, 1 over n cubed is a convergent p series because we've added 5 to the denominator. We've got a fraction with denominators that are a little bit bigger than the denominators of 1 over n cubed, which means the terms of this 1 over n cubed plus 5 series are all going to be less than or equal to the terms of this 1 over n cubed series. Okay, 1 over n cubed is a divergent p series because we have an exponent that's greater than 1. And so 1 over n cubed plus 5 is also going to be convergent. And yes, it's being multiplied by 3, but 3 times a convergent series is also going to be convergent. So this is going to be convergent, and you would say by the comparison test, okay, in comparison, comparing to 1 over n cubed. All right, the next one here, you may look at it, you may kind of, psych yourself out a little bit here at first, but one of the things you need to remember, this is going to burn people a lot, especially if you don't recognize it. You really need to be checking to see what the individual terms of your series approach, okay? And as n becomes very large, notice I've got an n squared term in the top and I've got an n squared term in the bottom. Those n squared terms are going to totally overpower that -1. And so over time, the terms of this series are basically going to approach n squared over 3n squared, which is 1/3. Okay, so as you go farther and farther out in your series, each of the terms are getting closer and closer to 1/3. If you add a third, plus a third, plus a third, plus a third, you just keep adding numbers that get closer and closer to a third, the individual terms are never approaching 0. Okay, this is an nth term test problem. The nth term is approaching 1/3. The nth term is not approaching 0. If you have individual terms that aren't approaching 0, your series is not going to have a sum. Okay, so again, you can't say the individual terms approach 0, and that means that my series is convergent. We don't necessarily know that because we know, for example, we have p series that are convergent. We have the harmonic series that has individual terms that approach 0, and it's not convergent. However, in this particular case, this is divergent, okay, by the nth term test because the individual terms never approach 0. We just keep adding 1/3 on to infinity, and that's not going to add up to any set total.